So many years ago, my family visited Cape Canaveral in Florida. And we went on some boring bus tour, and then there was an alligator, which was exciting. And then at some point, my parents said, "Hey, Erica, do you want to go see the decommissioned Saturn V? It looks like this." And it was hot and humid, and I wanted to go back to Disney World. So I said, "Will it be air conditioned?" And they said, "Yes." So I said, "Okay, let's go." So we go over there. And the problem with these pictures, everyone has seen these pictures, right? The problem with these pictures is they don't prepare you for the fact that rockets are actually really big. Like, they're actually just enormous. And you can imagine my surprise when this happens. This is 14-year-old Erika and the smallest dimension of the Saturn V. It is unbelievably large. It confused me. I didn't realize this was a real thing that happened. And I think this was the moment when it occurred to me that maybe space was big. And also that maybe space was interesting. And today I'm going to talk to you about human space travel, specifically some of the challenges that human space travel faces when it comes to fuel. So let me sort of introduce the problem to you now. So suppose we want to have a human mission to Mars, and then we want to bring our humans back from Mars. That's the hard part. So with a Saturn V, big as it is, it will get you to high Earth orbit. And then at high Earth orbit, you need more fuel. Okay, so let's say we have more fuel, and you get to Mars. Then at Mars, you need more fuel to come back to Earth. But whatever fuel you're using at Mars, you had to get it there in the first place, and to do that, you need more fuel. And you see we have a problem, which is that the farther away from Earth you venture, the more compounding fuel costs you face as you use fuel to transport fuel, and it's prohibitive. And maybe you can think of some ways around this. Maybe we could use solar sails and not need to use fuel at all. Maybe we could mine asteroids for fuel and not have to carry it with us. There's all sorts of really interesting ideas, and one of them was something I encountered during my high school science competition days, which is called the Interplanetary Transit network. And the basic idea here is that rather than using some big rocket to blast our way from point A to point B, instead, we're going to think really carefully about the path we're going to take so that the gravity and movement of all the planets in the solar system will pull us toward our destination. And that's very abstract. So let me give you an example of the consequences this has in the solar system today. Here's a graph of some stuff in our solar system. The horizontal axis is distance from the sun. So sun's on the left, then we have some planets. Vertical axis is just how elliptical the orbit is. And somewhere in between Mars and Jupiter is the asteroid belt. But we know more about the asteroid belt than just this. We know the orbits of lots of asteroids in the asteroid belt. And something unbelievably cool happens when you plot each asteroid as a dot on this graph. Look at this. Isn't this the coolest graph? Like, what is going on? There are gaps in the asteroid distribution. There are particular distances from the sun where there are no asteroids. What is going on? And here's what's happening. So if we look at this big gap at 2.5 astronomical units from the sun, if there was an asteroid there, it would go around the sun once every 4 Earth years. Meanwhile, Jupiter orbits the sun once every 12 Earth years. And that means Jupiter and our asteroid are in sync. Every 12 years, our asteroid will see Jupiter off in the same spot. Then it'll go around the sun 3 times, Jupiter will go around once, and it'll see Jupiter off in the same spot again. There will be a pattern of Jupiter's gravity pulling and pushing on that asteroid. And over hundreds of thousands of years, that pattern will repeat itself and push that asteroid off of its orbit so that the pattern goes away and they're no longer in sync. And each of these gaps, they're called Kirkwood gaps, is caused by a resonance between the orbit of an asteroid and the orbit of a heavy planet. Think how many Saturn V's this would take. There are many asteroids that are just way heavier than anything we're thinking about sending into space, and they're unpropelled, yet Jupiter is able to move them around with its gravity. And this is the effect that the Interplanetary Transit network is taking advantage of, the fact that you can use the gravity of planets to manipulate the orbits of objects. And of course, there's a catch, which is that it takes forever. So in the top maneuver, this is something that'll save you 20% of your original fuel cost, but it takes over 200 days as opposed to the original 4 to 5 days. And in another sort of unrelated but also a fuel-saving strategy, you can save almost 90% of the original fuel, but it takes years rather than days. But the fact that the numbers in this time required column are high does not mean that these paths are useless. The fact that we're thinking about these paths now means we're considering new types of space missions that we just never thought of before. And with our human space travel problem, we can solve our compounding fuel issue like this. So remember I said the problem was we're using fuel to transport fuel. So instead, we're going to use these really slow but very fuel-efficient paths to transport our fuel. So before we launch our humans, we start launching booster packs, chemical rockets, into space, and we slowly pre-position them along the path we're going to take later, like breadcrumbs. And then 5 years later, we launch our humans. They blast right through, picking up all the chemical boosters, enjoying the benefits of fast chemical rockets without the compounding fuel costs. And I'm going to close by giving you an idea of just how much this helps. So if our spacecraft with all the humans and all the cargo weighs 50 metric tons, this is very conservative, by the way, then we would need to launch 3,000 tons into low Earth orbit if we're not pre-placing our fuel, which is a lot. If we do pre-place the fuel, sort of using the strategy I suggested, we only have to launch 600 metric tons into low Earth orbit. And that is an order of magnitude different. That is bringing space travel, human space travel, to the far reaches of our solar system an order of magnitude closer to reality. Thank you.